for knowledge? No need to worry, because we, from Team Aurora, are going to share to you about the internal processes that shape the Earth. It includes plate tectonics, magmatism, anisostasy, and orogeny. Therefore, I want you to find a good connection. Sit back, relax, fasten your seatbelts, keep your eyes and ears with us, because today we are going to explore the internal processes that shape the Earth. So what are you waiting for? Come and learn with Team Aurora.
Good morning, everyone. Are you all doing well this morning? Okay, I hope you are. Now, can you look around you and describe me what formations or structures are you seeing? Are you seeing mountains, rock formations, perhaps a volcano? Okay. Now, well, today we will all learn about how some structures around us came to being. Before that, let us all watch this video.
Flying past the Earth at this time, we see a vast gray ocean beneath a red-tinted sky, punctuated by volcanoes and small land masses. And unlikely as it seems, life may have gained a foothold already. That life in the oceans that gave birth to it may actually be vaporized many times by cataclysmic bombardments, which have slowed but not yet stopped. Earth has begun to take on its final form, a crust, a skin so thin it would be less than a sheet of paper were the Earth the size of a basketball. And under that, a molten semi-solid mantle that boils in extreme slow motion. And finally, two cores, a liquid iron core pulsing out a magnetic field that helps shield us from a deadly cosmic wind from our sun. And a solid nickel and iron inner core. By now, the remarkable process of plate tectonics has kicked into gear. Though how and when it started exactly, we do not know. For what follows next, you might want to strap yourself in. It's going to be a bumpy ride. Here's how it might have happened. At first, Cretans and one continent called had the planet all to themselves. Then, around 500 million years later, Antarctica took shape. About another 500 million years passed before Atlantica formed. The continents roamed separately until, about 1.8 billion years ago, Antarctica collided with what is now Eastern Antarctica to form Nina. Then Nina, Atlantica, and collided 1 billion years ago, forming the supercontinent Rodinia. After about 300 million years, the three landmasses separated and came back together in a new configuration, Pangaea. Pangaea came apart too. When Pangaea split, and Atlantica split up too. If you're confused, join the club. Even the Earth seems confused. All of this movement made for a host of unlikely neighbors way back when. North America's eastern seaboard once rubbed shoulders with Chile. California and Australia were neighbors, if not connected. And Brazil was either connected to Nigeria or very close. Run the Earth time machine backwards, and you can see why. But no matter how many times you run the demolition derby of the continents, a question remains. What the hell is driving them? Hell, apparently. The force driving the plates is the slow movement of the super-hot semi-solid mantle that lies below the rigid plates. Like hot soup, magma boils in slow motion. Superheated magma rises to the surface, begins to cool, and then sinks back down to the bottom of the pot, where it is reheated and rises again. This cycle is repeated over and over to generate what scientists call a convection cell, or convective flow. But where's the heat source keeping our earthy soup performing its circular gymnastics? Well, most of it is left over from the spectacularly energetic collisions and gravitational crushing that created the Earth to begin with. It's still trapped down there, and it wants it out. And there's something else in the molten depths that makes it pretty hot real estate. Radioactive material. The belly of the beast has plenty of uranium and other radioactive elements, all of which release heat as they decay. That decay has significantly slowed the rate at which the Earth is cooling. So what does this mean at the surface? Two things. First, magma being burped up along the ridges, those places like Iceland where the Earth is tearing itself asunder, is pushing the plates in their respective continents apart. Second, what goes on at the other end of those plates, the collision zone, may be equally important. Here, where the heavier plates dive under the lighter ones, yanked downwards by gravity, they haul along their plates back into the oblivion of the mantle. That's what we know, or what we think we know. But the details of what's going on in the deepest parts of the Earth that drive the engine of plate tectonics, we may never know.
After watching the video, what ideas came to mind? What is plate tectonics? Well, I know that all of us have heard about plate tectonics since we were in elementary. From the deepest ocean trench to the tallest mountain, plate tectonics explains the features and movements of Earth's surface in the present and the past. Plate tectonics. By definition, the word plate in geologic terms means a large slab of solid rock. Tectonics is part of the Greek root for to build, and together the terms define how the Earth's surface is built up of moving plates. Now, plate tectonics is a theory that the Earth's outer shell is divided into several plates that glide over the mantle. These plates, or so-called tectonic plates, are rigid segments of the Earth's lithosphere that moves separately from those surrounding it. This theory attempts to explain as to how the movements of the Earth's lithosphere have formed and landscaped features we see across the globe today. Now let us first differentiate lithosphere from asthenosphere. Lithosphere is strong, cooler, and rigid outer layer, which includes the crust and the uppermost part of the mantle, while the asthenosphere lies below the lithosphere, which is part of the mantle. This region is hotter and malleable enough to allow movement. Now, when we talk about malleability, it is the capability of being shaped or changed to take on a new form. The principle of plate tectonics. The key principle of plate tectonics is that the lithosphere exists as a separate and distinct tectonic plates which float on the asthenosphere. Now, the relative fluidity of the asthenosphere allows the tectonic plates to undergo motion in different directions. Now, as I have said earlier, the tectonic plates are the rigid segment of the Earth's lithosphere. These tectonic plates can include continental crust or oceanic crust, and typically a single plate that carries both. Now, the distinction between continental crust and oceanic crust is based on the density of constituent materials. The oceanic crust is denser than the continental crust because it has less silicon and more heavier elements than the continental crust. As a result, oceanic crust generally lies below the sea level, while the continental crust projects above sea level. How many tectonic plates are there in the world? Actually, there are many tectonic plates in the world. and 7 of these are considered and identified as primary plates: the North American, Pacific, Eurasian, African, Indo-Australian, South American, and Antarctic plates. Among these plates, Pacific Plate is the largest, and most of it lies underneath the ocean. A lot of you may ask, how does plate tectonics works? To answer that question, let us proceed to the mechanisms or driving forces that propels the movement of tectonic plates. Actually, there are 3 main driving forces identified that cause the movement of the Earth's tectonic plates: the mantle convection and the gravitational forces slab pull and ridge push. Mantle convection. This is the most studied and identified as the main source of energy for movement of tectonic plates due to the continuous rising and sinking, or what we call convection, of molten materials from the mantle. Now, the heat source for convection is said to be the decay of radioactive elements in the mantle. Now, as these convection currents of molten materials transmit energy to the Earth's asthenosphere, a new lithospheric material is pushed up towards the Earth's crust. This is usually shown at mid-ocean ridges where younger land is pushed up through the ridge, causing the older land to move out and away from the ridge, thus moving the tectonic plates. Now, gravitational forces. This is the secondary driving force for movement. Slab pull. It is the pulling force of gravity caused by the sinking or subduction of cooler and denser plates of the lithosphere into the asthenosphere. Now, for example, if more than half of the tablecloth lies off the table, eventually the rest of the cloth will be pulled and be draped over the table. And this goes the same with slab pull. When there is this subducted slab, the weight of the subducted slab may drag the rest of the tectonic plate towards the trench. The third driving force is the ridge push, also known as the gravitational sliding, and it exists because the ridge occurs as a result of convection in the mantle. Therefore, as convection currents cause a new material to rise, the older land near the ridge are being pushed away to give way of a younger land, and this is observable in the seafloor spreading. Now we can say that the lands near the ridge are the younger ones, and the lands farther from the ridge are the older ones. There are 3 types of plate boundaries, and these boundaries are characterized by the way the plates move relative to each other. As foreknowledge, these plate boundaries are associated with geological events such as earthquakes and topographic features such as volcanoes, mountains, and trenches. First, convergent plate boundary. It occurs where 2 plates move towards each other, with one plate overriding the other. Now, in this type of plate boundary, there is these 2 plates, the overridden plate and the overriding plate. Now look at the example picture. The right plate is the overridden plate, which is driven back into the mantle and destroyed. And during this process of subduction, the earthquakes and volcanic activities are generated in the left plate, which is the overriding plate. As mentioned earlier, a tectonic plate can either be continental or oceanic. Now, there are 3 types of convergent boundaries occurring between them. First is between oceanic and continental plates. Second is between 2 oceanic plates. And third one is between 2 continental plates. So, number 1, oceanic versus continental. The oceanic plate subducts under the continental plate since it is denser. Because of this, a trench and continental arc are formed. Number 2, oceanic versus oceanic plates. One of these plates subducts and a trench and island arcs are formed. The last one is between two continental plates, and when this happens, one plate subducts and a mountain range is formed. Therefore, the common structures formed by convergent plate boundaries are volcanoes, mountain ranges, island and continental arcs, and trenches. The perfect example of this is the Pacific Ring of Fire, where the majority of the world's spectacular and most active volcanoes are located. The second type is the divergent plate boundary. It occurs where two tectonic plates move away from each other, which is driven by the magma rising from deep within the mantle. Any volcanic activity that occurs in this boundary creates a new land or lithosphere along with a cold spreading ridge. So the structures formed by this type of boundary are the rift valleys, mountain ridges, and oceanic ridges. The famous example of a structure that is formed by this type of boundary is the East African Great Rift Valley. The last boundary type is the transform plate boundary. It occurs where two plates slide past each other horizontally. Earthquakes are generated along this type of plate boundary due to stress buildup. Importantly, the lithosphere is preserved along. It is not created nor destroyed as it is at convergent and divergent plate boundaries. Therefore, structures formed with this type of boundary are fault lines, thin linear valleys, and splitted river beds. The most popular example for this is the San Andreas Fault in California. I am ending this discussion with a reminder that no matter what type of boundary we have, we give credit to the movement of tectonic plates in the Earth's lithosphere, the formation of beautiful landscape features we see across the globe today. Once again, good morning. This is Yanisa Joyce Mabutas reporting. Thank you for listening.
Good day, everyone. I'm going to discuss about the development of theory of plate tectonics implication to biogeography, the plate reconstruction, and plate tectonics on other celestial bodies. Let's start with the development of theory. So what is plate tectonics or plate tectonics itself? This theory states that Earth's solid outer crust, the lithosphere, is separated into plates that move over the asthenosphere, which is the molten upper portion of the mantle. Oceanic and continental plates, which is the 7 continental plates, come together and interact with boundaries all over the planet. You may wonder, how did the theory of plate tectonics all started? Well, around the start of 20th century, various theorists unsuccessfully attempted to explain the many geographical, geological, and biological continuities between continents. But in 1912, the meteorologist Alfred Wegener described what he called continental drift, an idea that culminated 50 years later in the modern theory of plate tectonics. Before we go through, let us know first who is Alfred Wegener. So Alfred Wegener is a German polar researcher, geophysicist, and meteorologist born in November 1, 1880 and died in November 1930 at the age of 50. He studied physics, meteorology, and astronomy at the University of Berlin. During his lifetime, he was primarily known for his achievements in meteorology and as a pioneer of polar research. But today, he is most remembered as the originator of the theory of continental drift. Also, there were awards and honors named after him. The Alfred Wegener Institute for Polar and Marine Research in Bremerhaven, Germany, was established in 1980 in Wegener's centenary. It awards the Wegener medals in his name, the crater Wegener in the Moon, the crater Wegener on Mars, and the asteroid 29227 Wegener. The European Geoscience Union sponsors Wegener Medal and honorary membership for scientists who have achieved exceptional international standing in atmospheric, hydrological, or oceanic sciences defined in their wildest senses. for their merit and their scientific achievements. Wegener's work was initially not widely accepted, in part due to lack of detailed evidence. The Earth might have a solid crust and mantle and a liquid core, but there seemed to be no way that portion of the crust could have moved around. Despite much opposition, the view of continental drift gained support and lively debate started between drifters or mobilists, which is the proponents of the theory, and the fixists, which is the opponents. So how does Wegener continental drift theory become the first step into developing the modern plate tectonics theory? Alfred Wegener was making serious arguments for the idea of continental drift in the first edition of The Origin of Continents and Oceans. In that book, he noted that how the east coast of South America and the west coast of Africa looked as if they were one attached. Wegener was not the first to know this, but he was the first to marshal significant fossil and paleotopographical and climatological evidence to support this simple observation. Wegener argued that all continents are once joined together in a single landmass and had since drifted apart. The mechanism could have been caused by drift or the centrifugal force, and speculated about seafloor spreading and mid-ocean ridges. Then, in 1953, American physicists Maurice Ewing and Bruce Hazen discovered that through these underwater ranges ran a deep canyon. In some places, the canyon, called the Great Global Rift, came very close to land. The rift appeared to be breaks in the Earth's crust, but perfectly fitted breaks like joints made by a carpenter. The rift outlined chunks of the Earth's crust which were named tectonic plates. 6 large and several smaller plates make up the surface of the globe. Most of the world's earthquakes and volcanoes occur at the plate's edges. The large plate containing most of the Pacific Rim accounts for 8% of the earthquake energy of the planet. This finding supported Alfred Wegener's theory of continental drift. There are also other theories that supported Wegener's idea of plate tectonics. In 1965, Tuzo Wilson, who had been a promoter of the seafloor spreading hypothesis and continental drift from the very beginning, added the concept of transform faults to be the model, completing the classes of fault types necessary to make the mobility of the plates on the globe work out. In 1967, at the American Geophysical Union's meeting, W. Jason Morgan proposed that the Earth's surface consists of 12 rigid plates that move relative to each other. 2 months later, Xavier Lippincon published a complete model based on the 6 major plates with the relative motion, which marked the final acceptance by the scientific community of plate tectonics. Thus, plate tectonics theory all started on Wegener's continental drift theory that even not taken seriously during his time, but then later on proved by various related studies that supported his ideas. Now, you all know how plate tectonics theory developed. This time, I'm going to discuss about the implications of plate tectonics to biogeography. Continental drift theory helps biogeographers to explain the disjunct biogeographic distribution of present-day life found on different continents but having similar ancestors. The position of movement of tectonic plates, some of which emerge through the oceans as lands, influences the distribution of life on Earth. Separation and connection of land and ocean have long been viewed as central to biogeography because they can influence the distribution of species through biological exchange. More precisely, changes in the continuity of habitats can influence rates of gene flow among populations and thus affect patterns of speciation and ecological assemblage. Features including land bridges, sea barriers, the mountain ranges, join or sunder populations. Deep-sea hydrothermal vents, volcanic islands, and changes in topography resulting from plate tectonics influence environmental conditions that in turn may mediate evolution. One type of evidence presented in support of continental drift by Wigner and others was paleobiogeographic, the widespread distribution of certain fossil animals and plants across landscapes that are now disconnected. See Figure 1. The founding concept of continental drift was that most of the Earth's land had formerly been connected in a single supercontinent called Pangaea. Fossils of Permian age indicate that Pangaea existed more than 250 million years ago, and modern evidence support this. In fact, the cave fossils occur primarily across the southern part of this continent, a region usually referred to as Gondwana or Gondwanaland, and it is noteworthy that this term was also used by land bridgers who also envisage a former extensive continent, parts of which subsequently disappeared. The found fossils are Mesosaurus, including a small number of meter-long marine reptile species recorded in early Permian time. It is said that Mesosaurus could not have crossed the Atlantic, but this is speculative, and at least one popular river source incorrectly states that these were freshwater reptiles. Next is Lystrosaurus included, a debated number of species of pig-like land reptiles less than 1 meter long. Then Cynognathus was a meter-long predatory mammal-like reptile usually treated as one species that existed in early to mid-Triassic time. Last is the Glossopteris, was a group of woody gymnosperm plants with wide but mostly southern distribution in the Permian. Another implication to biogeography is the land bridges and sea barriers. Plate tectonics can result in the connection of formerly disjunct land areas and simultaneously the sundering of marine environments through volcanics, accretion, orogenics, and deformation. Although land bridging has been largely rejected from consideration of ancient biological history of Earth, younger example shows its influence. The Central America, or Panama, Isthmus between North America and South America is a narrow strip of land that finally shut off the equatorial link between Atlantic and Pacific Oceans in the late Pliocene. The several tectonic plates intersect in this region, and their interaction appears to have led to the formation of numerous volcanic islands starting at about 5.5 million years ago. Sediment accumulation between these islands is one mechanism proposed for the land bridge. Closure forced the Gulf Stream to carry warm equatorial water into the northern Atlantic Ocean, where it influences the composition and ecology of regional marine biota. Separation was accompanied by other environmental change, appealing on the Pacific side to have increased while salinity has increased in the Caribbean. Around Central America, populations of marine creatures, even seabirds, and that are reluctant to fly overland were split between Western Atlantic and Eastern Pacific communities. On land, isthmus led to changes in rainfall and climate patterns and facilitated the exchange of land creatures. Many animals are inferred to have moved between continents and contributed to biotic mixing and thus elevated biodiversity in Central America. There are other more implications like formation of mountains, deep-sea hydrothermal vents, and formation of volcanoes. Next, let's find out about plate reconstruction. So what is plate reconstruction? It is the process of reconstructing the position of tectonic plates relative to each other or to the other reference frames, such as the Earth's magnetic field or groups of hotspots in the geological past. This helps determine the shape of makeup of ancient supercontinents and provides a basis for paleogeographic reconstructions. The evidence of plate reconstruction was the study of past plate motion up to the present plate motion. Plate motions, both those observable now and in the past, are referred ideally to a reference frame that allows other plate motions to be calculated. For example, a central plate such as the African plate may have motions of adjacent plates referred to it. By composition of reconstructions, additional plates can be reconstructed to the central plate. In turn, the reference plate may be reconstructed together with the other plates to another reference plate frame such as the Earth's magnetic field as determined from paleomagnetic measurements of rocks of known age. Since Earth is not the only planet in our solar system, we come to think if Earth is the only planet with tectonic plates. Well, on the terrestrial planet except Earth, scientists found that there was no presence of plate tectonics. Mercury cannot undergo plate tectonics since it is a uniplate planet, as we know that there should be separate plate for this to happen. Mars and Venus has found with volcanoes, but scientists was not pretty sure because plate tectonics needs liquid water and both planets has none of or scars. Venus is the most similar to Earth regarding tectonics, but has a very different tectonic style due to possible lack of water on the planet, causing a change in the rheology or elasticity of the rocks to make them more likely to fold than develop tectonics. More water in the chemical makeup of rocks means the rocks move more easily in the response to forces upon them, meaning they do not break easily and they are more elastic. Mars has a single plate that is thick and old but geologically diverse, containing lots of rock types. And jovial planets are all gas planets, so tectonics doesn't occur in this planet. But not specifically on one of the jovial planets, scientists found a possible tectonics on one of Jupiter's moon, Europa. Jupiter's icy moon Europa, regarded as perhaps the solar system's best bet to host alien life, keeps getting more and more interesting. Big slabs of ice are sliding over and under each other within Europa's ice shell. A new study suggests that the Jovian satellite may thus be the only solar system body besides Earth to possess a system of plate tectonics. So that's all.
Do you see a real volcano in real life? Have you ever wondered how the magma is formed? Today, we will tackle about the magmatism. What is magmatism? It is emplacement of magma within and on the surface of the outer layers of a terrestrial planet, which solidifies as igneous rocks. It does so through the magmatic activity or igneous activity, the production, intrusion, and extrusion of magma or lava. Volcanism is a surface expression of magmatism. In this picture, you will see the flow of magmatism. from the partial melting origin of magma until the volcanic gases mix with the atmosphere. What is magma? Magma is extremely hot liquid and semi-liquid rock located under Earth's surface. It is the molten or semi-molten natural material from which all igneous formed. This magma can push through holes or cracks in crust, causing a volcanic eruption. It is also contains a small amounts of dissolved gases such as water vapor, carbon dioxide, and sulfur. The high temperatures and pressure under Earth's crust keep magma in its fluid state. Origin of magma. The origin of magma has been controversial in geology, almost from the beginning of the science. Based on the scientific evidence, Earth's crust and mantle are composed primarily of solid, not molten rock. Although the outer core is fluid, its iron-rich material is very dense and remains deep the earth. Geologists conclude that magma originates when essentially solid rock located in the crust and upper mantle melts. The most obvious way to generate magma from solid rock is to raise the temperature above the level at which the rock begins to melt. As a rock is heated, minerals with the lowest melting points tend to start melting. While the melting continues, minerals with higher melting points began to melt, and the composition of magma steadily approaches the overall composition of the rock from which is derived. Most often, melting is not complete, and this process is known as a partial melting. Partial melting produces most, if not all, magma. The important consequences of partial melting is the production of magma with a higher silica content than the original rock. There are three basic types of magma. First is basaltic or mafic. Next is andesitic or intermediate. And lastly, rhyolitic or felsic. And these three basic types of magma has a different mineral compositions. In this table, we will see the compositions of magma. There are three types of magma: the basaltic, andesitic, and rhyolitic. The solidified volcanic rock of basaltic is basalt, while its solidified plutonic rock is gabbro. Next is the andesitic solidified volcanic rock is andesite, while its solidified plutonic rock is diorite. Lastly, the felsic or rhyolitic solidified volcanic rock is rhyolite, and its solidified plutonic rock is granite. In this table, we will see also the chemical compositions of each type of magma. Basaltic has 45 to 55% silicon dioxide, high in iron, magnesium, and calcium, while it is low in potassium and sodium. Its temperature is 1000 to 1200 degrees Celsius, while its viscosity is low and its gas content is also low. Next is the chemical composition of andesitic. It has 55 to 65% of silicon dioxide, intermediate in iron, magnesium, calcium, potassium, and sodium. Its temperature is 100 to 1000 degrees Celsius, while its viscosity is intermediate, same as its gas content. Lastly, The chemical composition of rhyolitic. It has 65 to 75% silicon dioxide, low in iron, magnesium, and calcium, while it is high in potassium and sodium. The temperature is 650 to 800 degrees Celsius, while its viscosity and gas content are high. The nature of volcanic eruptions. Volcanic activity is commonly perceived as a process that produces a picturesque cone-shaped structure that periodically erupts in a violent manner. Although some eruptions are very explosive, many others are not. What determines whether a volcano extrudes magma violently or gently? The primary factors include the magma's composition, its temperature, and the amount of dissolved gases it contains. To varying degrees, these factors affect the magma's viscosity or the stickiness of the magma. The more viscous the material, the greater its resistance to flow. For example, syrup is more viscous than water. Magma associated with an explosive eruption may be thousands of times more viscous than magma that is extruded in a quiescent manner. Viscosity of magmas. Viscosity is the resistance to flow or the opposite of fluidity. It depends on composition, temperature, and gas content. Higher silicon dioxide content magmas have higher viscosity than lower silicon dioxide content magmas. The lower temperature magmas have higher viscosity than higher temperature magmas. When heating syrup, you will notice that it will slowly turn into fluid or less viscous. It is because of the effect of temperature on its viscosity. So, there are factors affecting viscosity. The mobility of lava is strongly influenced by temperature. As a lava flow cools and begins to congeal, its mobility decreases and eventually the flow halts. A more significant influence on volcanic behavior is the chemical compositions of magmas. Magmas that produced by basaltic rocks contain about 50% silica, whereas magmas that produced by granitic rocks contain over 70% silica. Magma's viscosity is directly related to its silica content. The more silica in magma, the greater its viscosity. Due to high silica content, rhyolitic or felsic lavas are viscous, or it means very viscous, and tend to form comparatively short, thick flows, while the basaltic or mafic lavas contains less silica, tend to be more fluid, and have been known to travel distances of 150 kilometers or 90 miles or more before congealing. So in Hawaiian eruptions, the magmas are hot and basaltic, so they are extruded with ease. But highly viscous magmas are more difficult to force through a vent. The vent may become plugged with viscous magma, which can result in a buildup of gases that produce an explosive eruption. However, a viscous magma is not explosive by itself. It is the gas content that puts the bang in a violent eruption. High temperature and low near surface pressures, these gases will expand to occupy hundreds of times the original volume. Very fluid basaltic magmas allow the expanding gases to bubble upward and escape from the vent with relative ease. As they escape, the gases will often propel incandescent lava hundreds of meters into the air, producing lava fountains. Such fountains are mostly harmless and can cause great loss of lives and properties. Eruptions of fluid basaltic lavas, such as those occur in Hawaii, are relatively quiescent. This picture in the right corner of the slide is a picture of the eruption that happened in Hawaii. Highly viscous magmas impede upward migration of expanding gases. The gases collect in bubbles and pockets that increase in size until they explosively eject the semi-molten rock from the volcano. The result is a Mount St. Helen or Mount Pinatubo in the Philippines. To give idea about the result, here are some pictures. In the upper right corner is the Mount St. Helen, while the lower left corner is the Mount Pinatubo that can be found in the Philippines. So the viscosity of magma plus the quantity of dissolved gases and the ease with which they can escape determines the nature of a volcanic eruption. We can already understand the gentle volcanic eruptions of hot fluid lavas in Hawaii and the explosive violent eruptions of viscous lavas from volcanoes such as Mount St. Helens.
So let's proceed. When does volcanic eruption happens? Volcanic eruption happens when lava and gas are discharged from a volcanic vent. The materials associated with a volcanic eruption include lava flows, gases, and pyroclastic materials. Lava flows. When magma reaches the surface of the earth, it is called lava. Since it's liquid, it flows downhill in response to gravity as a lava flows. Different magma types behave differently as a lava flows, depending on their temperature, viscosity, and gas content. There are types of lava flows. The first one is Pahoehoe flows. It is balastic lava flows with low viscosity start to cool when exposed to the low temperature of the atmosphere. This causes a surface skin to form, although it is still very hot and behaves in plastic fashion, capable of deformation. Pahoehoe flows tend to be thin and because of their low viscosity, travel long distance from the vent. A flows. Higher viscosity, basaltic and andesitic lavas also initially develop a smooth surface skin, but this is quickly broken up by flow of the molten lava within and by gases that continue to escape from the lava. This creates a raw, clinkery surface that is characteristic of a AA flow. Gases. Magmas contains varied amounts of dissolved gases held in the molten rock by confining pressure. Volatiles is the gaseous components of magma. Gas gives magmas their explosive character because the gas expands and pressure is reduced. The gaseous portion of most magmas is believed to make up from 1 to 6% of the total weight, with most of this being water vapor. Gas is composed of 70% water vapor, 15% carbon dioxide, 5% nitrogen, 5% sulfur, and a lesser amount of chlorine, hydrogen, and argon. Sulfur compounds are easily recognized by their pungent odor and because they are natural source of air pollution. Pyroclastic material. If the magma has high content and high viscosity, the gas will expand in explosive fashion and break the liquid into clots that fly through the air and cool along their path through the atmosphere. Alternatively, blast out solid pieces of rock that once formed the volcanic edifice. All of these fragments are referred to as pyroclasts, hot broken fragments. Loose assemblages of pyroclast called tephra. Depending on size, tephra can be classified as bombs, blocks, lapilli, or ash. Volcano is a successive eruption from lava from a central vent result in a mountainous accumulation of material. Volcanic landforms are controlled by geological processes that form them and act on them after they have formed. There are three main types of volcanoes, namely composite volcano, cinder cone volcano, shield volcano. Shield cones are broad, slightly domed volcanoes built primarily of fluid ballastic lava. Most of the shield volcanoes have grown up from the deep ocean floor to form islands or sea mounts. The best example of shield cones are Hawaiian chain, Iceland, and the Galapagos. Cinder cones, it is also called scoria cones, are built from ejected lava fragments that take on the appearance of cinders or clinkers as they begin to harden while in flight. It have a steep slopes composed of pyroclastic materials. Composite cones or stratovolcanoes are large, nearly symmetrical structure built of interbedded lavas and pyroclastic deposits. It produced some of the most violent volcanic activity often associated with violent eruption is a Noe ardente. Noe ardente is a fiery cloud of hot gases infused with incandescent ash that races down steep volcanic slopes. In addition to violent eruptions, large composite cones may generate a type of mud flow referred to by its Indonesian name, lahar. Lahar occurs when volcanic debris becomes saturated with water and rapidly moves down steep volcanic slope, generally flowing gullies and stream valley. Take a look at the two pictures and see the difference between Noe ardente and lahar. Craters and calderas. Craters are circular depressions, usually less than 1 kilometer in a diameter, that form as a result of explosion that emit gases and ash. Calderas are much larger depressions, circular to elliptical in shape, with diameter ranging from 1 kilometer to to 50 km. Calderas form as a result of collapse of volcanic structure. The collapse results from evacuation of the underlying magma chamber. Effusive eruption. Effusive or non-explosive eruption are favored by low gas content and low viscosity magmas. If the viscosity is low, non-explosive eruption usually begin with fire fountains due to release of dissolved gases. Lava flows are produced on the surface and these run like liquids downslope along the lowest areas they can find. If the magma emerges along the fracture, it results in a fissure eruption, often called a curtain of fire. Lava flows produced by eruption underwater called pelulavas. If the viscosity is high but the gas content is low, then the lava will pile up over the vent to produce a lava dome or volcanic dome. Observe the different types of effusive eruption. Explosive eruptions are favored by high gas content and high viscosity magmas or andesitic to rhyolitic magmas. The explosive bursting of bubbles fragments the magma into clots of liquid that cool as they fall through the air. These solid particles became pyroclastic or volcanic ash. Clouds of gas and tephra that rise above a volcano produce an eruption column that can rise up to 45 kilometers into the atmosphere. Eventually, the tephra and the eruption column will be picked up by the wind, carried for some distance, and then fall back to the surface as a tephra fall or ash fall. This type of eruption is called Pellenian eruption. If the pressure in the bubbles is low, the eruption will produce an eruption column only a few hundred meters high, and most pyroclastic materials will fall too close to the vent to build a cinder cone. This type of eruption is called Strombolian eruption and is considered mildly explosive. If the eruption column collapses, a pyroclastic flow will occur wherein gas and tephra rush down the flanks of the volcano at high speed. This is the most dangerous type of volcanic eruption. The deposits that are produced are called ignimbrites. If they contain pumice or pyroclastic flow deposit, if they contain non-viscular blocks. Most active volcanoes are associated with plate boundaries. Active areas of volcanism are found along oceanic ridges where seafloor spreading is occurring in the divergent plate boundaries. In vicinity of ocean trenches where one plate is being subducted beneath another in the convergent plate boundaries. In the interiors of plates themselves or intraplate volcanism, rising plumes of hot mantle rock are the source of most intraplate volcanism.
Hi guys, it's Mrs. Russell, and I wanted to talk to you a little bit more about isostasy. This is a concept that we introduced in class today, but I did want to create a video talking about it in a little bit more detail. Isostasy explains how the lithosphere is floating on top of the asthenosphere and what those two layers look like whenever you were to put them in a picture. So I'd like to explain this concept by first using an example of a boat in water. If I drew my boat in the water, you would see that the boat is floating in the water. That is because the boat is less dense than the water. The boat is less dense and the water is more dense. Let's pretend I added 3 tons to my small boat. What's going to happen? Well, it's not going to sink all the way, but it definitely is going to dip down further into the water than it did before. So with less mass, it's less dense. With more mass, it's more dense. It's still less dense overall compared to the water because the boat is still floating, but it does dig deeper into the water. Well, what if I took that mass away? Let's say I took 2 tons back. Well, as you can imagine, the boat is going to pop up out of the water a lot more than when it had the 3 tons. Because I just took some of its mass away, making it less dense. Again, all 3 boats are still less dense than water. How do I know? Well, because all 3 of them are floating. But this boat right here, the middle boat, is the most dense out of the 3 boats. Well, how do I know that? Because it's dipping the deepest in the water. So you're probably thinking, Miss Russell, how are boats relating to the layers of the earth? Well, we talked about the layers of the earth, in specifics, the crust and the mantle. We learned that the crust is the outermost region and the mantle comes second. The crust is the layer that refers back to my example of the boat, because the crust is floating on top of the mantle. And the areas where we had more mass and our boat actually was digging deeper down into the water, that's areas on Earth where we have landforms that have more mass. Thus, they have more density and they dip deeper into the mantle of the Earth. So as you can see here, some continents. And on the continents, we have landforms. This looks like a mountain range. The mountain range has more mass, more density, and so it dips deeper into the mantle. Does it actually go past the mantle? No, because the mantle overall is still more dense than the crust. So the crust has different amounts of density, but it still overall is less dense than the mantle, so the crust is going to float. And if we get into even more details, we learned this term lithosphere. Lithosphere is a fast way to refer to both my crust layer and the top of the mantle. So as you can see in this picture, here's the crust, my oceanic right here, and here's some continental crust, and then back to my oceanic. Well, looking at my crust layer, this is not a perfectly straight line because underneath this mountain of continental crust, I have more density and more mass, and so this region is going to dip deeper in the asthenosphere. Isostasy explains how the lithosphere is floating upon the asthenosphere. There are regions of the lithosphere that have more density, for example, mountain ranges, that dip lower into the asthenosphere, but even so, they are still less dense than the asthenosphere, so they float.
Good day everyone. So you have seen on the video an introduction to isostasy. So before we proceed, let me introduce myself. I'm Irami S. Chavez and today we will talk about isostasy. What is isostasy? Isostasy is derived from the Greek word isos, which means equal, and stasis, which means stand still. It is a rising or settling of the Earth's lithosphere, and it can be observed if Earth's strong crust or lithosphere exerts stress on the weaker mantle or asthenosphere. The importance behind it is a principle that Earth's crust is floating on the mantle, like a boat in a water, rather than resting on a mantle like a boat on the ground. So what causes isostasy? Isostasy occurs when the buoyancy force pushing the lithosphere up equals the gravitational force pulling it down. The more stress applied to the Earth's crust, the more adjustment the Earth's crust will make. The same with the boat. The more weight it carries,
the more it goes deeper into the water. Now let's go to the models of isostasy. First is the Airy-Heiskanen model, where different topographic heights are accommodated by changes in crustal thickness, in which a crust has a constant density. Next is the Pratt-Hayford model, where different topographic heights are accommodated by lateral changes in rock density. Then the last one is the Vinning-Minnis. So you can see in the figure, Vinning-Minnis has a color green font. The Vinning-Minnis or flexural isostasy model is where the lithosphere acts as an elastic plate and its inherent rigidity distributes local topographic loads over a broad region by bending. Airy and Pratt isostasy are statements of buoyancy, but flexural isostasy is a statement of buoyancy when deflecting a sheet of finite elastic strength. Ice here. Greenland is an example of isostasy in action. The Greenland landmass is mostly below sea level because of the weight of the ice caps that covers the island. If the ice cap melted, the water would run off and raise sea level.
What is orogeny? Orogeny or orogenesis derives from the Greek oros, which means mountain, and genesis, which means origin or mode of formation. Orogeny refers specifically to deformation imposed during mountain building. Although mountains form in a variety of ways, most geologists associate orogeny with continental-sized mountain systems that develop along an entire continental margin as a result of the convergence and accretion of two or more tectonic plates. The term mountain building implies that the rate of surface uplift is greater than the rate of erosion, such that over time a lowland area evolves into mountain system. Orogeny includes a collage of processes such as magmatism, which generates continental crust, rejuvenation and recrystallization by metamorphism, wherein metamorphic belts occupy the orogenic core, deformation to produce major structures of orogenic belts, and sedimentation, where the mountain building activity takes place through the transportation of large volumes of sedimentary material. What causes orogeny? Orogenies may result from subduction, terrain accretion, the underthrusting of continents by oceanic plates, continental collisions, the overriding of oceanic ridges by continents, and other causes. The energy for orogeny is derived from horizontal compression, gravity, heat, and climate-driven erosion. Together, these energy sources disturb the thermal structure of the lithosphere and create stresses strong enough to produce folds, frost folds, strike-slip faults, normal folds, and other if one plate is pushed or subducted beneath the other. Where do orogenies occur? Lots of frosting and folding occurs in the pre-existing continental crust during an orogeny, inland from the subduction zone and a volcanic arc. This folding and folding creates a thickened area of crust called a fold and thrust belt. Did you know that Himalayas mountain is one of the many examples of orogeny? The geology of the Himalaya is a record of the most dramatic and visible creations of modern plate tectonic forces. The Himalayas, which stretch over 2,400 kilometers, are the result of an ongoing orogeny, the result of a collision between two continental tectonic plates. 250 million years ago, India was a large island situated off the Australian coast and separated from Asia by the Tethys Ocean. The supercontinent Pangaea began to break up 200 million years, and India started a northward drift towards Asia. From about 50 to 40 million years, the rate of northward drift of the Indian continental plate slowed to around 4 to 6 centimeters per year. This slowdown is interpreted to mark the beginning of the collision between the Eurasian and Indian continental plates, the closing of the former Tethys Ocean, and the initiation of Himalayan uplift. The Eurasian plate was partly crumpled and buckled up above the Indian plate, but due to their low density or high buoyancy, neither continental plate could be subducted. This caused the continental crust to thicken due to folding and faulting by compressional forces pushing up the Himalaya and the Tibetan Plateau. The continental crust here is twice the average thickness at around 75 kilometers. The thickening of the continental crust marked the end of volcanic activity in the region, as any magma moving upwards would solidify before it could reach the surface. The Himalayas are still rising by more than 1 centimeter per year as India continues to move northwards into Asia, which explains the occurrence of shallow focus earthquakes in the region today. However, the forces of weathering and erosion are lowering the Himalayas at about the same rate.